This is part 3 of the Chapter 2 summary for the Deep Learning book, authored by Ian Goodfellow and others as presented on screen here. In this video, I'm going to continue from where I left off previously, having reviewed Singular Value Decomposition. In particular, we're moving on to the application of SVD method for generating a matrix pseudo-inverse. Once again, these topics are somewhat new to me, and so this video will be more informative with regard to the topics at hand, rather than just being a summary. Alright, so I thought it would be best to start this video with a review of some basic matrix inverse principles. So as discussed in my previous video, which reviewed basic linear algebra concepts, one of the most prominent and common applications of linear algebra is to solve a system of linear equations by representing them in the AX equals B format. If you recall, the process to do so requires computing the inverse matrix of A, which then allows you to isolate for your unknowns and compute them with a matrix multiplication. The problem here is that the inverse can only be computed when the matrix is square with a non-zero determinant. So I find it easy to understand those limitations using a mathematical approach for the former and the intuitive approach for the latter. So for the condition that a matrix be square, you can see that the condition is necessary by following through the math with a matrix that isn't. The definition of the matrix inverse is that it can be multiplied on the left or right to yield the identity matrix. The characteristic of the multiplication being commutative is inherent to the definition. Also keep in mind that the identity matrix must be square by definition, so that when you multiply something by it, it's not the same, or rather it is the same, as not doing any operation at all. That's what the identity matrix is. So if we imagine we had an n by m matrix, then if we imagine its inverse exists and multiply it on its left side, it would have to be of size m by n to yield a square matrix, regardless of what the values would be to actually have that math follow through. But that could exist. So far so good, a matrix can be found which when multiplied yields the identity matrix. The problem is that if we take that same matrix and multiply it on the right side, the result is an identity matrix of size n as opposed to m, which we had before. So while the identity matrices of different sizes are obviously similar, they simply aren't the same mathematical entity. This means that the characteristic of multiplication being commutative is not present for a non-square matrix, so the inverse doesn't exist. So for the second condition of the inverse to exist, that the determinant be non-zero, I think the best way to understand that is to consider it visually. So the determinant of a given matrix is the factor by which that matrix transforms or changes the space of it changes a given area in space. What I mean is the stretch or compression factor of an area or a volume or a higher order volume. So if a transformation reduces even one dimension to zero, one dimension of space to zero by compressing it to nothing, then the resulting factor for that dimension, the factor to which it's being stretched or compressed, is zero. This can be interpreted as meaning that all data in that dimension is lost, as it's been compressed out of the entity. This is because the vector, or area we're transforming, could have been at any of infinite points along that dimension that we compress, but after compressing it, there's no way to know where it was along that dimension. This can be interpreted mathematically from the fact that once we've scaled down to zero in this way, there is no number that we can multiply by zero to give another number that isn't zero. Anything multiplied by zero is zero. It's the great leveler. I recommend the video by 3 Blue 1 Brown on matrix inverses to help visualize this, link in the description. So before going back into the pseudo-inverse method, I thought it would be good to touch upon left and right inverses. One point that may have stuck out to you in the second last slide's discussion was that it might seem wasteful to throw out the inverse we almost had just because the multiplication was not commutative. If you consider that the result of the identity matrix is the most important characteristic of an inverse, then it seems there would be value in the inverse that we saw, which could be constructed for just the left side. And this is the case. The inverses for just one side or the other side of a matrix are the left and right inverses, and these are useful tools which open the door for more possibilities. So non-square matrices actually can be inverted. Whereas earlier we were saying, in my other videos we were saying only square matrices can be inverted, there is this construct of the left and right inverse for non-square matrices. These are considered separately though. So knowing this, you might think of it as a bit of a chicken and egg problem. You can either think of left and right inverses being subcases of the general inverse for a square matrix, or you could think of the inverse of a square matrix as being a special case for a matrix that has both left and right inverses, and they happen to be equal to one another. So it should be noted that not every non-square matrix has two different inverses, one for left and one for right. That's not the case. Actually, tall matrices have only a left inverse, wide matrices have only a right inverse. Also, for a given matrix, the left inverse or right inverse will only exist if the matrix has full column rank or full row rank respectively. This means that the set of column vectors or the set of row vectors making up the matrix must be completely linearly independent for the inverse to exist. And this might be thought of as an alternative for the non-zero determinant condition for inverse existence. See, for a square matrix, it needs a non-zero determinant to have an inverse. But since we're dealing with non-square matrices don't have determinants. So that's what I mean when I say that you could think of this condition of full row rank and full column rank as being a kind of analogous to the non-zero determinant condition, since the determinant can't be computed for a non-square matrix. Okay, so we'll quickly go over the math for how this is done, how you can compute a left or a right inverse. For either case of tall matrices or wide matrices, the matrix is multiplied with its transpose, such that the result is the smaller possible square matrix. Then the inverse of that matrix is taken. Lastly, a shift in perspective allows for the transpose that was originally multiplied by the original to be included in what we consider the left or right inverse. So really, the left and right inverse encapsulate a sequence of transformations on the original matrix at hand, which yield the inverse in total, the identity matrix, after you multiply it with what you started with. So overall, we're converting a matrix to being square by multiplying it by its transpose, and then multiplying that square matrix by its own inverse to yield the identity matrix. Okay, so now that we've looked at some of the fundamentals of matrix inversion, we can see how the singular value decomposition can be used to compute a so-called pseudo-inverse for a matrix. This is actually a very powerful tool for generalizing matrix inverses beyond merely left and right for non-rectangular matrices, non-square rather. So the fundamental idea is that since the SVD, singular value decomposition, provides us with a way to express a matrix using other terms, we can express that matrix inverse by manipulating those other terms and the algebraic expression making them up. So in particular, we take those terms and we put them in reverse order when we multiply them, and for each one we take the inverse. So what allows us to make headway with this idea is the defining characteristics of the matrices used in the SVD, that the first and third are orthogonal and the second is diagonal. These characteristics make it very easy to invert them to our benefit. So if you recall, the inverse of an orthogonal matrix is equal to its transpose. And furthermore, when we take the economy approximation, which is mathematically equivalent to the original, we reduce the diagonal matrix in the middle to a square, which makes it easily invertible. So where the SVD defines our matrix as being equal to UdV transpose, we can then express the inverse of our matrix as V d inverse U transpose. And the reason for that is because our V vector is orthogonal, so its inverse, we want to take the inverse, its inverse is its transpose. So since it was already transposed, we're taking the transpose once again, it just becomes V. Our D matrix is square, so it's straightforward to take the inverse, we can do that. And our U matrix was also orthogonal, and so its inverse is its transpose. So we take the transpose of U. And we put it in this particular order, which is reversed from its original order, so that when we put it up against itself, all these multiplied terms yield the identity matrices, and we end up with basically the definition of the inverse, that it's multiplied by that item on the left and it yields the identity matrix. So that's why it's sequenced the way that it is. And as a regular inverse for a square matrix, just your regular vanilla square matrix, as with that, you can use this expression for the inverse to compute the linear system of equations, ax equals b. But to do so, to apply the methodology in this way, it isn't merely feasible. It also has a couple of characteristics which, in most cases, make it optimal. So to see this in action, we'll consider the two general types of matrices, tall and skinny versus short and wide. So first, we'll look at the general case of a short and wide matrix. In fact, this kind of matrix is called underdetermined. You can understand that name when you contextualize it in a frame of a system of linear equations. This kind of matrix corresponds to a problem where there are many more degrees of freedom than there are constraints. As such, the solution space is very large, and there are infinite variations of solutions that can be made for the system. A physical analog or analogy to visualize this situation could be to imagine trying to hit a target but having barriers in the way. So I'll just take a moment to sketch that out, to make this idea of systems of equations and constraints and degrees of freedom hopefully a little bit clearer than it might be in abstract. So if we imagine, as you can see on the draw pad over here, if we imagine we have a target which we want to hit, and we have a barrier in the way. In fact, instead of making this target a single point, we'll just say it's an entire wall, back wall. And so now imagine we have a laser over here, and so this laser is shining, and we want to be able to hit the wall. And let's say that all we can do is move our laser along this rail. So what is this? This is an analogy for the system of equations such as I described, linear system. And the way that is, the way I'm thinking about it, is that you have here you have 1 degree of freedom. This can slide up or it can slide down. So you could think that you have one variable, that's a degree of freedom, that you choose your position, you choose where you want to be along this bar. And then you have a constraint. So the constraint is this barrier. So it's something, we can represent it with, just one equation. We can say this is this constraint. It's encapsulated by this equation. And then lastly, you have your target. So we want to hit the target. This is kind of how the analogy would work for this idea. So with 1 degree of freedom, you can see how being able to move this laser up and down, there's always going to be a solution where you can just find the gap in this barrier and shoot it through the gap. So if the gap was instead over here, if our gap was over here, then a modified x position, say right over here, could have the solution. So now, how does this work with degrees of freedom and more constraints? So imagine this. We could say, in a higher level scenario, imagine we have, instead of just one barrier like this, we have multiple barriers. And so I'll draw them as kind of sheets. So imagine we have multiple barriers. And imagine that these have areas, regions within them that you could pass through, holes like Swiss cheese almost. And so the idea is that now, instead of having only one line along which you could move your laser, 1 degree of freedom, now imagine that your laser is on a kind of a 2-rod type of system where you have 2 degrees of freedom. So now you could put your laser anywhere on this area and try and hit the target. And so you can imagine how there may be, at some position of x1 and x2, a coincident pathway between 2 of these different holes in these sheets, which then allow you to get through. So it might be over here. So you can see how 2 degrees of freedom and 2 constraints, you could actually have a solution. And then what we started off talking about was the underdetermined system. So again, underdetermined system is characterized by fewer constraints than we have degrees of freedom. So for a trivial case of a undetermined system, imagine this. Imagine that you had the same kind of idea, lasers, and trying to hit the target, but this time instead, let's say we have just 1 degree of freedom for the constraint. So it's just a line like this that you can't that's obstructing your pathway of your target. And then let's say you wanted to hit this target, and this was actually a sphere. We'll just say this is a sphere. And now instead of just being able to shoot in one direction with 1 degree of freedom, let's say we can have 2 degrees of freedom, and we are trying to get our laser to that target. Not only can we be within this span and this point of x such that any solution in here will work to get through that open range and in our barrier. But not only that, but if we simply move over to the right, now all of a sudden any point over here at all will just pass right by, because our constraint was just one-dimensional. So if our constraint is one-dimensional, we can just go right around it. It's hardly even in the way. So you can see how literally any 2 points you pick to place your laser on this entire axis, as long as it's not on that one slice which aligns with this, any other points will allow you to just go right by. It's like trying to shoot on an open net in some sport. And so this is the fundamental characteristic of an underdetermined system. There are infinite possible solutions, because you could choose any point over here as a starting point and just go right by this trivial constraint, which is hardly even in the way. In this case, it's just like a pole being in the way, and you could just shoot around it. So that's the reason we have infinite potential solutions, is because you're free to pick any one of these points, and because we're working in continuous space, there's infinite points all over this place. So that's an analogy for the underdetermined system in physical space. Alright, so having established that an underdetermined system often have infinite solutions, we can get back to the strength of the Moore-Penrose Pseudo-inverse method using the SVD. So the strength of the method is that the solution vector it provides will be the single vector in the entire infinite solution space that has the minimum 2 norm, also known as the Euclidean norm. This is super helpful because it allows us to hone in on a solution instead of drowning, mathematically speaking, in infinite and thus undefined solutions. So in particular, this is really helpful because it's more common than not in real life that we want to minimize the decision variables we have, and not the quantity of decision variables, but the values that get attributed to them. For example, if the system of equations represented a physical system, or described a physical system, and then the decision variables represented some forces or energy that you apply to the system with the intent of reaching a target state, then of course it's desirable to find the solution that demands the minimum energy, the minimum force to be applied to reach your target state. So that's the kind of solution that this method provides. So it's very handy and helpful. So that's how this method can be applied to an underdetermined matrix. On the other hand, we have tall and skinny matrices. So these are called overdetermined. To use a similar analogy to that we had before, imagine that this matrix represents the constraints in a scenario where we're trying to point the laser at a target. So an overdetermined system would have too many constraints and not enough degrees of freedom. So for example, you can imagine a scenario where you have the following. We could simply build on our original scenario by saying, what if we have our target and we have 1 degree of freedom? So we can choose where this laser is along this rail. And then we have 2 constraints. So if we have 1 constraint here and 1 constraint here, well, obviously there's just no way to reach the target because these holes don't line up and we can only shoot in a straight line. And so you see how in this trivial example, although you can go to higher dimensions if you wish, such as we were looking at earlier, you can see how if there are more constraints in degrees of freedom, it's pretty much certain, almost certain, that you're going to have no possible solutions. Although you can imagine, even with this analogy, for example, that if these happen to line up, then it's still possible to have a solution, a potential solution. But that's not guaranteed that it's going to happen. And so typically, it's safe to say that you'll often have no solutions for an overdetermined scenario. But you can do some reading on Wikipedia to see when these other possibilities are the case. So in this kind of scenario, when our matrix is overdetermined, once again, the pseudo-inverse method is tremendously powerful because while there are no feasible solutions, this method still provides a solution. And in fact, it provides the solution with the minimum error. Specifically, it minimizes error as defined by the Euclidean norm of the difference between the left and right-hand sides of our equation, expressed as vectors. So I find that it's really valuable to understand this outcome intuitively, and following the mathematical process clearly shows that how this desirable minimum error outcome naturally follows from the method, since what's being done is that the solution vector, which is outside of our feasible space, is being projected onto our feasible space. So to see this, first let's just see how the math works out generally. After expressing the matrix A using the SVD, and then multiplying both sides by the pseudo-inverse, we immediately see that our solution, x tilde, is equal to the pseudo-inverse by B, the same form as we see with invertible square matrices that don't require exercising this method. But like we said, the premise of this method is that we're finding the solution with the minimum error. So what that means is that we're not actually solving for the x vector that yields B when we put it in our original equation. This is because there's no such thing. The premise of our problem was that there's no vector that would yield B. It's infeasible. So the question is, what is our solution actually giving us? So we can see what happens when we plug in our expression for x back into the left side from our original equation to see what our approximate solution really points to on the right side rather than B as it's expressed in the original equation. So after employing the SVD and pseudo-inverse on the left side, we can see that actually our result is equal to U times U transpose times B. And this is really important. We can't simplify this further as we were doing before because U transpose is not equal to the identity matrix. And if you recall from the video on the SVD, in full form the U matrix is square and orthogonal. But to really leverage the SVD for huge data sets, we use the economy form of the U matrix. And when we did this, oops, let me just go back to that slide there. Right. So, if you recall from the video on the SVD, in full form, the U matrix is square and not orthogonal. Pardon me, it is orthogonal. But to really leverage the SVD for huge data sets, we use the economy form of the U matrix. And when we do so, we chop off some of its columns. The result is that it's no longer square. In fact, it's overdetermined because we chopped off columns. And so the principle that the transpose is equal to the inverse does not hold true anymore for multiplying the transpose on the right side. And this is a really interesting outcome. For a square orthogonal matrix, the transpose is equal to the inverse, and that inverse isn't particular to left or right. But after truncating the original matrix, the orthogonal matrix rather, to make it over or underdetermined, the transpose of the truncated matrix is equal to its new left inverse or right inverse respectively. So if we truncate an orthogonal square matrix so as to make it overdetermined, what before the transpose, whereas before it was the complete inverse, now the transpose is the left inverse. But if we truncate a square matrix to make it underdetermined, then the transpose is the right inverse. So as a result, we're left with this expression that we can't simplify any further, but it's enough to provide us with a really strong intuitive understanding of how this method actually provides a result where none is perfectly feasible. So considering the result of computing U by U transpose as a matrix, which is itself a transformation, we know from algebra first principles that the result of multiplying a vector with a matrix is that the resulting vector will always be in the column space of the matrix. In this case, we can go even further than this. From the principles of the SVD, we know the columns of U form an orthogonal basis. Once again, this fact proves critical here because for a matrix containing an orthogonal basis, this equation, the matrix by its transpose, U by U transpose, is actually the function which projects a given vector onto this basis. I'm going to share a link in the description for a great video lecture from MIT on subspace projection. So really what the equation is showing us is that we're projecting B onto the subspace of U. We know from first principles of projection in linear fields that the result of this projection can only be that vector in the subspace U by UT, which has the least error when compared to our target outcome. Okay, so again, I'm just going to do a quick sketch to show this. So the notion is that, let's say our subspace is two-dimensional. So we have a vector A, and it's forming an orthogonal basis of two vectors. So if we draw 3D space, then the notion is that there's going to be some plane. So we could just draw a plane over here. So we could say the origin is cutting through right over here, and it's above these other axes. So the notion is that we have a subspace here. This is the subspace of A. And the question is then, what vector x, when transformed by the matrix A, will yield the vector B? So let's say that our vector B is actually up here. And if I just go straight down from the axis, let's say that this is actually above our plane. So it's not on our plane, it's above it. Now the problem is that, as we just mentioned, any vector you multiply by x, any vector you multiply by A, will inevitably yield a vector that's within the subspace. So that vector will inevitably be somewhere along on this plane surface. And so that's the premise of our problem. Since it's going to be on this surface, it simply cannot reach this point. But that point is what we're calling B. So AX cannot equal B. So as we were discussing, what's happening here is that we are actually computing for an X input, an X outcome, which, when transformed by A, yields not B, but the projection of B onto our subspace. And as we mentioned, that's the closest it can possibly get. So the projection of B onto the subspace, if we draw the B vector as just pointing to its spot, then the projection of B onto the subspace is the vector to the point which is as close as it can be to our subspace. So if there's its intersection with the space and it has these right angles with the surface of our subspace, then this vector over here, this vector pointing to this point, is actually what our x vector is yielding after being transformed with A. So we have this vector, which is A x tilde, and that's going to be equal to an approximate B. And the approximate B is actually the projection of B onto our subspace. And the difference between these two, this line right here, is the error. That's the difference between them. And so, as we mentioned, the solution that is provided by the SVD method and the pseudo-inverse is the solution for x tilde, which actually minimizes the norm of this vector. And naturally, we know from geometry that it's simply the point at which there will be perpendicular lines to the surface that then go to the point of interest, the original B that's unreachable. So that's a visual sketch of what this is doing. We're projecting the vector, which we can't make, B, onto our space. And then we're finding the x vector, which when transformed by A is equivalent to the projection vector. So actually, just quick note on the slide here, there should be an A right here. So A transformed by x tilde equals the projection of B onto the subspace. So this should be AX. So that's pretty much that. The reason this works perfectly for us is this. Since the matrix we're talking about, the product of U by U transpose, only has the same basis as U did on its own. U by U transpose has the same column space as U. Then this matrix has the same span as U. And the final step is to realize that, given the definition of the SVD, the matrix U is intended to contain a basis for the exact same span as the original matrix A. So this has to be the case with the SVD, or else how could we construct our A matrix with a different span, with a different basis? It's meant to emulate the basis. So that's how projecting B onto the subspace of U transpose has the same outcome as projecting B onto the subspace of A, because it's the same subspace. And so that's why it's yielding the correct vector that we want. So our takeaway is that what this whole computation does is that it gives us a solution vector, x, which instead of its transformation by matrix A guiding us to the static vector B, which is infeasible, the solution maps us onto the projection of B onto our subspace, which is by definition the closest we can get to an actual target vector B. So I'll leave this video off here. To recap, the singular value decomposition method offers us the opportunity to compute an inverse matrix where it wouldn't otherwise be possible. That is in the case of non-square matrices. Whether the matrix of interest is under or overdetermined, the SVD method offers a particular brand of solution, which for most applications is the best solutions we could ask for, by minimizing the error or by minimizing the values of our solution vector when there were infinite solutions before. So I hope that this video is helpful. Thanks for watching, and check out the links in the description for further reading if this wasn't clear. Take care.